Alright, so very good afternoon to everyone. A very good afternoon to all of you, my dear students. A very good afternoon to all of you. So guys, my name is Dr. Shankar Sir and I am your physics educator. मैं आपका physics educator हूँ and we are going to continue now with our journey of stress and strain. Okay, so we'll be continuing from here the journey that we have started in the domain of stress and strain, that is the properties of the solid. Okay, so guys, I'll give you a brief overview that what we have done till today. So on this channel, we have completed units and measurement. That is the first chapter of the physics, right? So you will be able to find all the videos related to this particular chapter on this channel. Okay, and you can complete this particular chapter in all the respects. If you follow the sessions on the channel, I have given you one short video also in which you can deal it is kind of a quick revision session there. Afterwards we have done the motion in 1D, that is motion in a straight line. We have completed it, right? Now during this I have given you the concepts of integration, the concepts of differentiation also. You can find it again on this channel. Okay, so all of the motion in a straight line is completed comprehensively. Afterwards we have done motion in a 2D, motion in a plane, right? We have completed this chapter also on this channel, and along with it we have done vectors, right? And now this is the concept. These are the chapters from the part 1 of the physics, right, of class 11. So I have started with the part 2 of physics of class 11th also, and we are now doing the properties of solids. Properties of solids, right? And in this we have done till some extent. So on this, you may see on this channel there are two videos. One is on Hooke's law, other is on the continuation of it, the elastic property, right? So in the last session guys, what we have been doing, we have been talking of the Hooke's law, and we have seen that how to utilize the Hooke's law and the Poisson effect to calculate the changes in dimension and stresses, right? So what we have done in the last session, so if there is a load P acting on a body, okay, and this is like this. So because in this particular part of physics we are dealing with the static equilibrium problems, this is B, this is D. So from Hooke's law we understood that the normal stress is equal to force upon area, that is P upon BD, and the deflection, so normal stress is proportional to the normal strain, and the normal strain is sigma upon E. So the normal strain is P by A, normal strain, or you can call it longitudinal strain. It is going to be P by A by E, right? Okay, and also we can write it like delta L upon L, that is P upon AE. So from this we come to know in the last session that delta L, that is the change in length, is PL upon A. PL upon A. I hope it is fine to everyone, right? In the last session we have seen this. Now along with it, so this is what we call as the longitudinal strain. We have discussed all this in the last session. Now what is going to be the lateral strain? What do we call as the lateral strain? So if I talk about the lateral strain, it is what? It is the lateral strain. Okay, so whenever a load, a normal load is acting in some direction, you will be having the longitudinal strain as well as the lateral strain, right? So lateral strain is the strain in the direction perpendicular to the direction of the load. Like for example, in this case, the lateral strain is going to be delta B by B and delta D by D. This is going to be called upon as your lateral strain. Okay, so there is one thing, that is the Poisson ratio. That is the Poisson ratio, and this Poisson ratio we denote by mu, or we can denote by the mu. My mu is not that good. This is my mu, and this is Poisson ratio is given as minus of lateral to the longitudinal strain. So in the last session, when you see of this particular properties of solids, so I have given you like how to deal with the deformations, load, stress, longitudinal, lateral, Poisson ratio, and everything. Okay, right? So we have dealt with it quite in a good way in the last session. So I hope you don't have any problem in this, right? So lastly, we have done some questions to understand that how we can use the stress thing, how we can use the strain thing. Okay. Okay. Now let's start by some questions so that you further understand these very concepts. Okay. So today we are going to have a big enough session and we'll be trying to, finish it off. Come. Now let's try this question. So the live students, you can answer me. Oh, it is gone out of the screen. Yeah. Yeah. Let's try to do it. I'm very sure we can do. All the live students, you can respond to me. See what we are trying to do. We are trying to understand the concept of it. Please go ahead. The live students. Can you guys please answer me? How can we do this question? See, today we are going to understand this topic, this chapter, in a conclusive way. I'll try to complete this thing today. Let's try. I'm very sure we can do. Please try. How can we answer the question? Please try to do it. I'm very sure we can do it. There's no problem at all. Please try it, guys. Now, what does it say? So it says that there are two identical circular rods of same diameter and same length are subjected to same magnitude of axial tensile force. All right, very well. One of the rod is made up out of mild steel, which has a Young's modulus of 206 GPa. So Young's modulus of mild steel is given as 206 GPa. Okay, wonderful. The other rod is made up of cast iron having the modulus of elasticity 100 GPa. So cast iron is having the modulus of elasticity that is 100 GPa. Alright, very well. Assume both the material to be homogeneous and isotropic. The axial force causes. So this is the very assumption you are taking in any problem that you are solving. See, in this equation also we are assuming that the material is homogeneous and isotropic. Okay, and the axial force causes the same amount of uniform stress in both the ends. Okay, that is well. The stresses developed are within the proportionality limit of respective material. Now, within the proportionality limit of the respective material, that means Hooke's law is valid, isn't it? Hooke's law is valid. This is the indication, or this is the hint that we can consider the Hooke's law to be valid. We can consider the Hooke's law to be valid in this case, right? Now, Hooke's law being valid, so can we enforce this formula? Delta is equal to PL upon A. Now, see, equation themselves says a lot about something, right? Equation themselves says a lot about something. So, see, in this delta is equal to PL upon A. So, can we write delta is proportional to 1 upon E. Delta is proportional to this 1 upon E, right? Delta is proportional to 1 upon E. Do you agree? Yes, sir. So delta is proportional to 1 upon E, and this is valid within the proportionality limit. This is valid within proportionality limit, right? This is valid within the proportionality limit, right? Within proportionality limit, that is within the Hooke's law region, right? Within the proportionality, within the limit of proportionality, it is mentioned very well, very clearly in the question, so we can use this formula. Now, please understand this. If we see this formula, delta is proportional to 1 by E. So, if I write the delta, now see from this, can you realize that lower the value of Young's modulus E, lower the value of Young's modulus E, higher will be the value of delta, isn't it? See, they are in inverse proportion. They are in inverse proportion. So, lower the value of E, higher will be the value of delta, isn't it? Okay. Lower the value of E, higher will be the value of this delta thing. Higher will be the value of this delta. Do you agree or not? Please answer me, guys. Yeah? Yeah? I hope this is fine to everyone. Right. Now, whose E is more, whose E is less? Can you tell me? Whose Young's modulus or the modulus of elasticity is more, whose modulus of elasticity is less. Now clearly we can see one thing. The modulus of elasticity, that is E of cast iron, is less than the modulus of elasticity of mild steel. Now from here, can I say, see, they are having the inverse relationship. So cast iron deformation will be more than the deformation of mild steel. Are you getting my point, Mira? But now somebody people will say, sorry, sir, cast iron is a brittle kind of a material. What is the brittle material? See, simply, see, if aluminium. So what is the meaning of brittleness? See, if you are putting force on some body and it do not elongate, it do not deform, and it directly breaks. Okay, like glass. Okay, if glass falls from some height, glass of so sir, we have steel glass at home. That is not I am referring to. Let's suppose we are having a steel glass and we are having a glass, right? And if both of them fell from the table, you see the steel glass is not going to break. Okay, it will not going to break, but the glass is going to break down, isn't it? Okay, okay. Or let's suppose we are having a cup of steel and having a cup of glass. If both of them fell from the same height, the steel glass is not going to break, but the glass cup is going to get broken. Okay, so that is the brittleness. It do not, deform but break. Okay, so now many students will say the cast iron is a brittle material. It is a common knowledge. So cast iron being the brittle material, how is elongation can be more than mild steel? So remember, this is valid. This is valid till proportionality limit. Okay, till elastic region. Proportionality limit means that the region of elasticity. Please try to understand it. See, whatever is the meaning of whenever we are referring to the elasticity and all this, basically we are dealing by default within the elastic region. So when talking in the elastic region, the cast iron will deform less than that of the mild steel for a particular amount of load. Okay, let's suppose on a body of cast iron and there is a body of mild steel. If you apply the load, same load on these two bodies, the cast iron is going to show you more elongation than the mild steel in the elastic region. Okay, than the elastic region. Okay, okay, is it fine? Right, right. Okay. Now, so what is elasticity? So when we say about elastic, so what is elasticity? If I try to explain the elasticity, okay, so see, when we see elasticity, basically two things that are we need to clear up, we need to understand. So the tendency or the tendency to oppose, the tendency to oppose any, the tendency of to oppose any, the tendency to oppose any change in the shape and size, change in the shape and size, okay, shape and size by a body. Okay, this is the first thing. Okay, so basically elasticity is a property inherent to the material due to which it basically resists its change in shape and size, right? So whenever something is trying to, or some force is trying to change the shape and size of a body made up of any material, it's a material property having this tendency to oppose this change and size of oppose the change in shape and size of the body. Okay, is it fine? Right? No problem. So this is fine only. Now talking about the second point. Talking about the second point. So elasticity also refers to it is the tendency of a body. It is the tendency of a body to regain its original configuration or regain its original shape, okay, regain its original shape after removal of the deforming force. Deforming force. Are you getting my point, beta? So see, two things are there. So whenever on a body some force is applied, whenever on a body some force is applied, now due to that force, what is going to happen? So see, I'll just show you one example here. Just I have something with me. This is the box of my laptop. Okay. Now see, this is a solid, no? So after this, we'll be starting with the fluid. That also it will help you. Now see, what is this elasticity? So when you are applying force on this very body, when you are applying the force on this, please have a look. When you are applying the force on it, I'll just you see see like this. Okay, so when we are applying the force, I think you can now see this more clearly. So when we are applying the force on this, see, when we are applying the force, it is this body is going like this. So this is shear. We'll come to shear and everything. Just try to understand the nature of the body. Now, when we are applying the force on it, it is resisting. It is resisting, right? Now, when I remove it, see, when I remove this force, it is coming back. It is trying to come back to its original position. Are you getting my point? So when when I applying force and see, when I leave it, you see, I am holding it like this, and now when I applying the force, it is coming back to its original shape. You see, like this. This is elasticity. Are you getting my point? This is nothing but this is the elasticity. I hope you have got this. Okay. I use my laptop box somewhat to show how this solid and fluids. I'll be explaining you the fluid from this only. Now let's come to the point. Okay, so you have seen like a solid body is there. So elasticity refers to these two things. One is, first of all, due to this property, any solid body opposes the change in its shape and size. So whenever a force, so force is something like, what is the nature of a force? What is force in physics or in any particular thing? So force basically is a thing which will do something. Okay, either it will displace a body, either it will deform a body, Right, whenever a force is acting on something, it will give something, something will happen because of the force, right? If the body is displacing, that we do the kinematics, dynamics part, right? If it is deforming, we come to this part, okay? Now, when a force is applied on a body and it tries to change the shape of the body due to the elasticity, due to the property of the elasticity of the material, basically our body, our material resists the changes in resist the changes in its shape and size due to the applied force or the deforming force. This is one aspect. The other aspect is as I demonstrated. So when you remove the force, when you remove the force, it is very likely that when you remove the force and the force applied is within the elastic region. So whatever we are talking here, we are talking, remember, within elastic region, within elastic region, okay. Now within elastic region, what happens? So if the force is well within elastic region, when you remove the force, when you remove the force, your body is going to regain its original shape, okay. It is going to regain its original shape. So whatever strain has happened, whatever strain has happened, whatever strain has happened, it is going to be reverted. It is going to be what? It is going to be reverted. Okay, you are going to revert that deformation, that strain, and your body is going to be back in the original condition. Now I have a question to ask to you. So if I ask you that we have a steel, we have a rubber, which is more elastic, is steel or rubber? So the live student can respond to me, is steel or rubber, right? You must have seen both. Okay. When I say steel, there is something coming in your mind. Okay, this is the steel. Every day we are seeing the steel so much, right? And rubber, obviously the same rubber that you have been using from quite a time now, right? Okay. The pencil rubber wala rubber, that rubber only. Now to that rubber only and steel, if I compare, which is more elastic? Okay, if I ask you that, tell me, my friends, that which is more elastic, what would you say? What would you say? Which is more elastic? Come. Which is more elastic out of steel and rubber? Please answer me, guys. Which is more elastic? Which will be more elastic? So, sir, obviously, sir, steel is more elastic, not obviously. Many students say yes, rubber is more elastic, sir. That is that we call it even elastic when we, in many states, in many places, you go to buy a rubber actually, and you say, "Give me some elastic," isn't it? You don't say, but to a physicist or to an engineer or to a someone who knows the physics, and if someone just like me, if someone comes to me and tell me to give some elastic, I would probably give him the steel, because steel is more elastic than rubber. Are you getting my point? Sir, how come, sir? We are thinking that rubber is more elastic. So no, guys, rubber is not more elastic than the rubber is not more elastic than the steel. Why so? So as I said, to see the elasticity of something, we need to understand is that to see the elasticity, it is basically the tendency. There are two things. It is the tendency to oppose any change in the shape and size of a body. Okay. So elasticity being the tendency to oppose the change in the shape and size of the body. Okay, so who gives you more resistance when some shape change or size change is happening in it? Is it the rubber or is it the you know is it the rubber or is it the steel? Now you would say, sir, we can clearly think that steel is resisting more. Steel is resisting more towards its change of shape and size, right? Okay. Now the second point, elasticity. So sir, rubber when we stretch and we leave the force, it is coming back to its original position, right? Okay. Now steel. So first of all, understand that we are talking within the limit of proportionality, the elastic region. Now, if the force is within the elastic region, and you apply the force in the steel and you remove it, it is instantaneously going to regain its original shape. Are you getting my point? Are you getting my point? Okay. So basically, from both the things, steel is the answer. So steel is more elastic than the rubber, because see, you cannot increase. So when we are talking about the elasticity, we are talking well within the limit of elasticity or elastic region or proportionality limit. So in these cases, the force cannot be beyond a certain point. Okay, if you apply the force beyond a certain point, there will be, there will be going to be the permanent shape changes. Understood? That is not what is happening here. So steel is more elastic. So see, basically, when we are commenting upon the elongation within the elastic region, when we are commenting on the elongation within the elastic region, we have to see the Young's modulus. Higher the Young's modulus, lower will be the deflection in the elastic region, and vice versa. Like for example, if I say aluminium, so aluminium Young's modulus is somewhere near 75 GPa. So it will show more elongation within elastic region than cast iron, and cast iron will show more elongation within the than the mild steel. Than the mild steel. I hope it is fine to everyone. Right? Okay. Now let's try one question. Very interesting. So in the last session we have done some simple questions. Now let's try this one. Let's see if we can do or not. Please go ahead. Please try it. Please try to solve the question. The live students can answer me. See, very, very simple. Please go ahead. Please go ahead. I'm very sure we can do it. Any live students who may want to answer this question, please go for it. I'm very sure we can do it. No problem at all, beta. Please try to do. See, there is nothing in this question that you can't do. Please go for it. See, very simple. Please try. So this is how physics works. Please do. Please do it. See, very interesting question. Please try to solve it. See, there is nothing in this question that you don't know. You just have to use some aptitude and you need to solve it. Okay? Please go ahead. Please try to do it. Very interesting question. A little bit different in from how you see the question normally. A little different. Please try to do it. I'm very, very sure we can do. Please go ahead. Please go ahead. Any answers? Please go for it. Hello, Rupesh G. Thank you. Yeah, any answers, please? See, I want you to attempt the question. See, in physics, you have to develop some aptitude, right? In this, you have to find the axial displacement. Please try finding it. See, I want at least one student do it, then I proceed. See, very interesting question. Normally, you don't find these kind of equations and these kind of questions, but see, when you do this kind of a question, definitely it is going to help you a lot. in understanding the concept and realizing the use of the formula. Okay. Please try answering it. Yeah, please try. I'm waiting only. I'm waiting. Please try. Please answer. Rupesh, no. Not the right answer. It isn't the velocity. Uh, Easy. Again, I would say, don't do that. I won't recommend it, my dear. See, for the maths you required for the NEET physics, I have taught on this chapter. You won't need anything more than that. Are you getting my point? You try solving this question, you wouldn't be needing anything more. A little math is required to solve the physics problems. Like you don't have to do that. Rupesh, in this we have to find the displacement. Basically, you have to find the deflection. Please try it. I'm very sure we can do. Please try. Ah, Edhi, we have discussed this before also, no? Isn't it? Haven't we discussed this before? Okay, okay, Pradipta. I'm waiting. No worries. Please do. So, Edhi, as I was saying, see, please understand this. I told this before also that see, you can study whatever you want, right? There is no stopping you, isn't it? Right? If you want to read any book of the physics, you can go. You can even read research papers also. हाँ कोई बात नहीं। आप एक काम करो, आप गूगल स्कॉलर पे जाओ, मेरा नाम लिखो उमा शंकर त्रिपाठी, आपको मेरे रिसर्च पेपर मिल जाएंगे 3 हाई इम्पैक्ट फैक्टर के। पढ़िए, कुछ समझ में आएगा तो बताइएगा। आर यू गेटिंग माय पॉइंट दोस्त? देखो, ये इससे अभी आपको कोई फ़ायदा नहीं मिलेगा। या तो आप नीट की प्रिपरेशन छोड़ दें, समझ रहे हैं आप? ठीक है, मतलब छोड़ दें, मेरा कहने का मतलब है कि अगर आपको बहुत डीप जाना है किसी भी सब्जेक्ट में, देखो कंपटीशन ऐसे नहीं निकलते, एक सब्जेक्ट में बहुत डीप चले गए, बाकी सब्जेक्ट का पता नहीं चल रहा है। गेटिंग माई पॉइंट? ठीक है, तो अभी ये ठीक वक्त नहीं है उस चीज़ के लिए। ठीक है, जब आप कंपटीशन की तैयारी करें, वो भी नीट, कितना लोग देता है नीट बताइए? हाउ मेनी स्टूडेंट्स आर अपेयरिंग एवरी ईयर नीट? बताइए, करते हैं इसके बारे में बात करते हैं। बताइए, हाउ मेनी स्टूडेंट्स आर अपेयरिंग द नीट एग्जामिनेशन एवरी ईयर? बताओ प्रदीप्ता, dear, meanwhile you try solving the question. Are you solving the question? Shall I solve it? Shall I solve it, or are you trying to solve? Did you get my point or not? Please try to do. Have you done it, Pradipta? Have you done it? Please tell me so that I can also proceed with the question. I'm waiting for you. Please tell me. Anyone who can answer this question? So it says a horizontal, let me do it now. So it says a horizontal bar fixed at one end, so x is 0, has a length of 1 meter. So we are having a horizontal bar somewhat like this. Okay, and the length of the bar is 1 meter. Okay, very well. So this is given as 1 meter. This is given as 1 meter. And the cross sectional area is 100 mm square. So area we are having 100 mm square. Is elastic modulus varies along the length. So now in the previous question, so first of all, please try to realize that how this question is different from the previous one. How this question is a bit different from the previous question, right? So all in the previous questions that we have done in the last session. Okay, so see, whenever we are trying to use this formula, Normally, we'll see that in a problem, the load is constant. Okay, area is constant, Young's modulus is constant, and length is constant, isn't it? Okay, but here you can observe one thing. So here we are given with a function of the Young's modulus. Okay, so here the Young's modulus is not at all constant, but it is changing with respect to x. It is changing with respect to x. So when the Young's modulus is changing with respect to x, my dear, it is changing with respect to x. Now here in this case, we have to find the displacement of the free end. Okay, so a force of 10 kilonewton being applied. Okay, so the load being applied on this is 10 kilonewton. Okay, now please understand this. We are having only one formula, right? We don't have any other formula to find the deformation, and this is the only formula. So PL upon A. Okay, but to use this formula, now to use this formula directly, all of it must be constant. But here in this case, E is not constant. It is varying. It is varying. Now please understand this. Whenever something is in variation, my dear, whenever something is varying, so whenever something is varying, something is in variation, we cannot do or apply the formula directly. Now we need to use the concept of integration that we have seen. That is why every time I say that do integration, do differentiation to some extent, right? Now here the E is varying. So when E is varying, see, just try to understand this one fundamental of physics. In this chapter or in any chapter, whenever you see that something is in variation, you always think of that we have to do somewhat mathematics and we have to do somewhat integration, right? Like in this case, E is varying, the Young's modulus is varying. Now, when the Young's modulus is varying, how you can deal with it? So, for that, what you have to do? Okay, so Young's modulus here is varying. So, when Young's modulus is varying, what we have to do? We have to think of the integration. So, are you trying this way, or is there any other way that you are trying to do it? Okay, okay. So you are still trying. Okay, okay. I'm waiting. No worries. No worries. Just let me know when you solve it. When your attempt is over, just let me know that you have attempted the question. All right? Sounds good? Any answer? Are you still trying? Okay, let me do it. So in the next question, you may try it because it's a lot of time has happened. Okay, now see, what is the concept? The key concept is that whenever in the physics you see there's some quantity being varying. Okay, so when some quantity being varying, what you can do, you can always take a strip. Okay, so let us take a strip of, a small thickness. So we are taking the strip here. This is a strip of a very small thickness, let's say dx. Okay, this is a strip of very small thickness, that is dx. Okay, see, now see, whenever anything like that happens, that the something is varying uniformly or the variation of it is given, you are analyzing any parameter or any physical quantity, you write that quantity or that parameter on that particular strip. Okay, so when I do for the strip, so can I write delta of a strip? That means that elongation or the deformation of a strip is PL upon A. So we have only one formula in the world. Okay, so when we are writing for the strip, we have to take the length of the strip, that is dx. So we have P dx upon A. Now if I integrate, see, if I integrate both the sides, so this will become delta. This will become delta. Now P is constant, A is constant, and this is given what? This is given as 1 upon E is given as 100 e to the power minus x GPA. Okay, GPA. So can I multiply it with 10 to the power 9 dx, because GPA I am converting it into the Pascal. Okay, I am converting it into the Pascal. Right? Okay, understood? And now let's put the value. So P is what? It is 10 kilonewton. So 10 kilonewton means 10 into 10 to the power 3. Area is 100 mm square. So converting 100 mm into meter. So it will become mm into meter. So it will become 10 to the power minus 6. 10 to the power minus 6, isn't it? Okay. 10 to the power minus 6, right? Okay, and now this will become 1 into 10 to the power 11. Okay, 1 upon 10 to the power 11, and e to the power minus x will become e to the power x dx. And what are the limits? So see, this is 1 meter, so x is 0 and at this x is equal to 1. So how we can put the limits? So we don't know this much integration. Please watch my video on this channel where I have explained the integration. All this concept I have explained. Okay, so this is going to be from 0 to 1. Okay, so when I integrate from 0 to 1 meter, what I'll be getting? So see how much zeros we are left with. So 10 to the power 4 and 11 minus 6, so it will become minus 5 and minus 5, and this is 1. So it is going to be, we are going to left with 10 to the power minus 3, isn't it? See, 4, 5, 6, and this is going 100 mm. So it is given as, okay, so see, this will become 1, 2, so 13, 10 to the power 13 and 10 to the power, so this will become 10 to the power minus 3, isn't it? Delta 10 to the power minus 3. And when you integrate e to the power exponential, it is going to be the same value. So it is 0 to 1. So it will become 10 to the power 3 e to the power 1 minus e to the power 0. E to the power 1 minus e to the power 0. So what is e to the power 1? Sir, it is 2.71, right? So you must remember the value of e. So it will become 10 to the power minus 3 and e to the power 0. So it is 2.71 minus 1. So basically it will become, delta will become 1.71 into 10 to the power minus 3 meter. So 1.71 into 10 to the power minus 3 meter, that means 1.71 mm, right? So what is the answer to this question? The answer to this question is 1.71 mm. So dear Pradipta, where you held up? What stopped you solving the question? Please answer me. What has stopped you solving the question? Can you answer it? Hmm? I hope it is fine to you now. Now let's try one question. Let's move ahead. So see now if Young's modulus is constant, you can clearly directly apply the formula and solve the question. Now let's suppose Young's modulus is not varying. Okay, Young's modulus is not varying. Let's suppose we are having something like that. So we are having, let's suppose, a tapered bar. Okay, let's suppose we are having a tapered bar somewhat like this. Sir, we have never seen such things in NCRT. And don't worry, in competitive examination, they can use any concept, na? So we are trying to understand this concept. Let's suppose this side the diameter is D1, this side the diameter is D2, and this is having a circular cross section. The length is L. The Young's modulus now is constant, and Young's modulus is E, and a force is applied here P. Now you need to get the deformation, elongation of the tapered bar. Okay. Can you get me the tapered bar elongation? Please go ahead. Please tell me. Yeah, please do. It is quite cold here. Okay. Yeah, Pradipta, you can please do. I'll wait, I'll wait. No worries. Huh. See, once you qualify the NEET, you can study anything what you want. Right? Or if you are so much interested in physics, why don't you pursue BSc? Plain BSc you do in physics. What is the problem? If you want to read physics, what is wrong? You do BSc in physics, then do MSc in physics, then qualify, then do PhD in physics. What is the problem? Who is stopping you? That is also a good career if that you want ultimately. Hmm? You can go in the research field of the physics, right? That also easy you can do. Okay, I'm waiting. How you are approaching it? Can you tell me? Please do. Please keep trying. No worries, no worries. I'll wait. I'll wait. Not a problem. Please do. Yeah, yeah. See, the concept remain the same. Yes, yes. Please take some time. See, these questions are not present in NCERT. That is one thing. But these can come, these can come in the examination because see, this follows the same Hooke's law, same everything, right? So basically, with this, one, this could be a question of this, right? Please try it. Take some time. Take some time. No worries. See, if at all you can, understand the approach, that is also fine. Please do. Yeah, please do. Yeah, yeah, yeah. Yeah, I'm waiting, waiting. You guys please try. I'll wait. I'll wait. No worries. No worries. Please do. I'm waiting for your answers. Please tell me when you are done, attempting it. See, the classes, these live classes are for, you know, live students. Okay, these classes are for live students. So, see, we are here to help you. So, if you are attempting, I have no problem in waiting. No worries. Okay, the students who are watching the recorded session, you can please forward the video. Okay, please don't mind it. Right. So you understand that when live students are there, so for live students, these live sessions are for the live student. You also come live, you answer, and whatever doubts will be there, that will be resolved right away. Okay. So I'm waiting for you to answer. Yes, some students are attempting. Yeah, please do it. Is it done? Students who are live. Students who are live, you can please tell me. You can do it. Shall I do? Okay, Akansha, you are unable to do it. Okay, I'll do. I'll do. No worries. What about you, Pradipta, and what is it? Cakewalk. You're little tricky, little tricky. Yeah. So, Akansha, have you tried? What do you do in this? You understood this question? How we did it? They'll just explain one thing to you. See, whenever we have to find the deflection, we only have one formula. In the case where load is normal, that is delta is equal to PL upon A, right? Now, in this question, I think you joined a little late. In this question, see what happened. In this question, see what happened. In this question, see what happened. In this question, Young's modulus was varying. Okay. In this question, the Young's modulus was varying. So see, please try to understand one concept that whenever something is varying, we have to prepare for integration. Okay, we have to prepare for integration, right? So see how we can do with the integration. Actually, just one moment. I'll just have to see on YouTube. We have to sometimes now be taking care of the yeah. Yeah. Oh, no, no. Now I'm solving it. You please observe the reply. Right? In the next question, you can try. Acha, acha, you are trying to solve. Okay, I'll just wait 2 minutes. Akansha, till by then, I'll just give you some hints. See, do you realize that in this case, what is happening? In this case, the diameter is varying. In the previous question, Young's modulus was varying. That is, the modulus of elasticity was varying. Okay, so meanwhile, the predictor is trying to solve the question. Uh, what you can do, you can please try to do this way. So in the last question, Young's modulus was varying. In this question, the diameter is varying. Right now, you have to see when. So what is the concept? When something is varying, we have to prepare for what? We have to try to prepare for integration, isn't it? We have to try to prepare for the integration, right? Now for integration, what you can do? Please try. I'm waiting. Please try. I'm waiting. No worries. So in this, see, the diameter is now varying. So when diameter is varying, see, anything that is probably varying. So in that case, always there is only one concept. See, first of all, realize that this is only this formula that ultimately have to be applied. We don't have any other formula, right? So ultimately, we must prepare or we must try to use this formula in the given circumstances. So let's take a strip, okay? And see why we are taking the strip, sir. So we are taking the strip because here the diameter is varying linearly. It is not constant. If at all the diameter is constant, we can right away use the formula and can answer. But here the diameter is not constant, but it is varying. So when the diameter is varying, my dear, when the diameter is varying, my dear, when the diameter is varying, my dear, so diameter being varying, so whenever something vary, we need to take care of the strip. We have to take a strip, then only we must proceed. Now see what happens. Now see what happens. So here I'll be writing d delta. I'll write the elongation of the strip. It will be p dx upon area. So I'll write ax e. E is constant. Now what is ax? Sir, ax is the area at the strip. Okay, area at the strip. So now what I can do? So I can write d delta c p upon x, p upon e. Now it is going to be dx upon 1 by a. So what will be the a, sir? It is pi by 4 because it is circular now. So pi by 4, let's call the diameter of the strip as d. So can I write it like this? 1 upon pi by 4 d square. Sir, why not you taking this d as constant? Array, see, d is varying only, na? So d is not constant. Okay, d is not constant. See, remember my point. Whenever something is in variation, whenever something is in variation, whenever something is varying, you need to take a strip and then you must prepare for integration. So see, can I write this d as, so see, now please understand this, how can we write this d? Now you see, if I take x from here, this is d2 and this is d1, right? This is d2 and this is d1. So what is the d going to be? So from d2 to d1, you can see that it is increasing. See, this is the general way. If something is varying linearly from one to another, okay, one to another, you are going to see that. Okay. Understood? Okay. So how it is? So from D2, so X I have taken from D2. So from D2, it is increasing. So how we can write it? See, D2 plus, if it would have been, if we would have written from D1, I would have subtracted because from 1 to 2, the diameter being decreasing. So see, from D2, it will become, see, D1 minus D2 of D1 minus D2 in the length of what? In the length of L, okay, in the length of L into X. See, this is the variation how you can write it. Okay. Okay. So from D2 it is going towards D1. So we'll write plus and then we have this D1 minus D2 upon L into X. So this is how mathematics work. Okay, so this is what we get from the rule of linear variation, right? Now you can put this d here, you can put this d here. So when you put this d here and integrate, so take all the common things, 4p upon pi e, and you will put it here. So integration 1 upon d2 plus d1 minus d2 of x upon L dx. So this is somewhat a little bit tricky integration, right? So we are not going to integrate it. I'll just give you the final result. So see, when you are integrating it, so you can remember it as the case of the tapered bar. Okay, you will get PLC. Very simple formula. Pi by 4 d1 into d2 into e. When you solve it, you are going to get this thing. Are you getting my point, Bida? When you are going to solve it, you are going to get this thing. Right? Is it fine? Please answer me if it is fine or not. Yeah? So see, whenever, see, and you can make comparison also. So see. So if there is a tapered bar, if there is a tapered bar, right? If there is a tapered bar subjected to a load P and its diameter is varying from D1 to D2. Its diameter is varying from D1 to D2. What is going to be the elongation of this bar if we try to solve it? So it will become, if the length of this bar is L, so this will become PL upon pi by 4 D1 D2 into E. PL upon pi by 4 D1 D2 into E. Okay. Okay, and for the prismatic bar, so see, you can see an analogy, right? Right. So if it is P acting here, and this is L, let's suppose this is L, and the dia here is D. Okay, the dia here is D. So here the elongation. So we call it prismatic. Prismatic means uniform cross section. So this is a prismatic. We'll call it a prismatic. The meaning of prismatic is that it is a uniform cross section bar. So the prismatic bar diameter will become PL upon pi by 4 d square into E. Okay, d square into E. Understood? Understood? I hope it is fine to everyone. Now, for same elongation, now see, if the tapered bar, I want the tapered bar. Now, what is the question? I want, now you answer me guys. If I want this tapered bar to be replaced by a prismatic bar, that is a bar of uniform cross section for same deformation, what shall be the diameter of that prismatic bar in terms of D1 and D2? Can you answer me? Please answer me. Please answer me. Live student. What am I asking? Any live student may try to respond to me. What I am asking. So I am saying that this prismatic bar having the diameter of D1, sorry, this tapered bar having the diameter of D1 and D2, we need to replace it for the same loading with a prismatic bar. What should be the diameter of that prismatic bar? Bole. Okay. So for same elongation, you need to replace, you need to equate them. Okay. Now when you will be equating them, so what you will be getting? So for the same elongation, that means prismatic bar and the tapered bar, if they have to have the same elongation, what you are going to get? So it will be PL upon pi by 4 d square E. This is the general formula. PL upon A we have been using quite a while now. And the tapered bar, it will be PL upon pi by 4 d1 d2 into E. So from here can we have d is equal to root over d1 d2. D is equal to root over d1 d2. I hope it is fine to everyone. Please answer me. Yeah. Is it fine? Agreed or not? Please answer me. Hmm? Wonderful. Wonderful. Okay. Now, this is what we call as, yeah, this question is solved. I think you are speaking of the previous question. Okay. So this is what we call as the geometric mean, isn't it? This is what we call as the geometric mean. Do you agree or not? So whenever we are having a tapered bar and we want to replace it with a prismatic bar, we want to replace it with a prismatic bar of same, for same elongation. There is one tapered bar having the diameters d1 and d2, and if we want to replace it with a prismatic bar, that means having the uniform diameter, then what shall be the relation? The relation should be d is equal to root over d1 d2. That means it must be the geometric mean. Understood? Okay. Now let's try one question. I'll just, so one question I can make. Okay. Let's suppose we are having a tapered bar like this. We are having a tapered bar like this. Now please understand this. we are having a tapered bar like this. This is let's suppose P load, this is also P, and the diameter here is 2 times D. So whenever we have the sign of phi, this is the diameter, and the diameter here is D. Okay. Now I'll write a question. So a student has calculated, एक बच्चे ने, एक स्टूडेंट ने क्या किया? A student has calculated elongation the elongation by considering it a prismatic bar, considering it a prismatic bar of mean dia, prismatic bar of mean diameter. Okay. Okay, mean diameter. Now what you need to do? You need to find the percentage. Find the percentage error. What you need to do? You need to find the percentage error. Now let's try this one. I'm very sure we can do it. Correct. Please try. Please try, guys. Correct. Very interesting question. Percentage error, you have to find percentage error. So what happened, this is, so let me explain the question. So we are having a tapered bar whose diameter at one side is 2 times of D and other side is D. A load of P is applied on this particular tapered bar. Now a student has calculated the elongation of this bar by assuming it a prismatic bar of mean diameter. Now you need to find the percentage error. Okay. Now when this happened, so now someone has assumed it a prismatic bar of mean diameter, that is average diameter. So definitely there will be some error in the calculation. Now you need to tell me what is the percentage error. Please go ahead. Please go ahead. Please try answering it. Please answer it. The live student, you may answer it. You may try to answer it. Please go ahead. Please answer. But the wrong answer. 33% you are saying. No, no, no. This is not the answer. Please try to attempt again. Please try attempting it again. Yeah, I'm waiting, waiting. 33% is not the answer. Yeah, yeah. Okay, okay. I'll wait. I'll wait. No worries. You take your time. No issues. I hope all of us know how to find the percentage error, right? Yes, sir. Obviously, we know. Please do. Any answer? Please answer. Just one moment. There's some technical issue. Yeah, Kumar. Hello. Sorry, there was some technical issue, some light issues, right? Okay. Yeah, yeah. But I'm waiting. You can please try answering. Please try answering this. I'm very sure we can do. Yeah, yeah, Kumar. I'll just explain. So this, okay, I'll explain. So see, Kumar, we just have understood this concept. So see, what we are talking, I'll just give you a brief about what we are doing here. So my dear, my name is Dr. Shankar Sir, and these are my brief credentials. So see, we are talking about the properties of solid. So you must be aware of the Hooke's law, right? So from Hooke's law, the stress is force upon area. Okay, and stress and strain are proportional within the limit of proportionality. So from here we get this formula, right? This. So like to solve the problem, we are having only this problem, this formula. Now what we have done, so in the simple question, obviously we can apply. In the simple questions we have seen in the last session. Okay, some simple questions we have seen in the last session, right? Now this was the previous question. Now in this question you see that Young's modulus is varying. Okay, Young's modulus is varying from 100 e to the power minus x GPA. Okay, it is having given with it is given that e is varying with respect to x. So what was my point? My point is, see, we have only one formula. Now, if something is variation, you always need to integrate. So when something, some physical quantity is in variation, what you can do? You can take a strip and integrate. So this is how we solve this question. In this, the Young's modulus was varying, so we put this value and everything, and we integrated, we solved. Now see, this is a tapered bar. In this, what happens? The diameter changes from one end to another end. It decreases linearly, right? It decreases linearly, and now we are interested in finding out the elongation of this particular bar when it is subjected to a load of P, right? Now in this you see the diameter is varying. So what we have to do? We have to do some integration. So for that what we have done? Sir, we have taken one strip. What we did? We taken one strip. Now when we once we taken the strip C, then we integrated. So see, we have written the elongation or the deflection on the strip. Okay, so what is the only formula we are having? It is PL upon AE. So the length of the strip is P dx, and the area there we are assuming it as AX and E. Now from this concept we have derived, and this is the formula that we have got. So tapered bar formula is PL upon pi by 4 D1 D2 into E if you want to find the elongation of tapered bar. Kumar, is it clear up to this point? Yeah? Please answer me if it is clear up to this point. Please give me a yes or no. Is it clear to this point? Yeah? Please answer me. Right. Now see, what does this question say? So question says that, and also see, if we relate the tapered bar with a uniform bar, what is going to happen? So see, for same elongation, the diameter of the uniform bar shall be root d1 d2. I just have equated these two formulas and find the d. Now in this question what it says the student has calculated the elongation considering it a prismatic bar of mean diameter. Now what the student have done? So student have considered, what a student have done? So a student has considered, you are trying. Okay, okay. Okay, I'll do this one, you try the next one. Right? Sounds good? Sounds good? Or you want to try? Anything, anything. Anything works for me. And please do subscribe the channel also. Shall I wait? Prayapta, you also please answer. Are you attempting the question? Okay, I'll do. Now see. So now the student has calculated the elongation by considering it a prismatic bar of mean diameter. So what the student have done? So student have must have used this formula. PL upon pi by 4. Now what he has considered, I'm solving. You consider that it's a mean diameter. So what is the mean diameter? So it is 2D, it is D. So do you realize that the mean diameter is 1.5 D whole of a square into E? So what the student have done, he has considered this one as a prismatic bar. Prismatic bar means a bar of uniform cross section and diameter of it being the mean diameter. So mean diameter will be 2D and this is D. So 2D and D, what will be the mean of it? It will be 1.5, isn't it? Right? Mean means average. So the average of it is 1.5 D square. Now definitely this is not the right way, so this will have some error, isn't it? isn't it? Do you agree, Kumar? This is going to have some error. Now we need to find the percentage error. So now this is having some error. So what we must do, sir, we must find the correct value. Okay, then only you find the percentage error. Na? See, if there is error in something, you need to find the percentage error. So you must have the actual value also. Now, what is going to be the actual value? So can I write the actual or the real or the correct one? So it will be PL upon pi by 4 pi by 4. So d1 into d2. What is the formula? See, pi by 4 d1 d2. So what is d1? It is 2d. It is d into e. So what is the real value? What shall be the actual elongation? It must be pl upon 2 pi by 4 d square into e. Right, so this is the real value. And what is the error one? The error value, it must be, see, 1.5 whole of a square. So it must be 2.25 PL upon pi by 4 d square into e. Now you tell me, my dear, you are having the error value, okay, the value in which the error is there. You are having the value in which there is no error. So when you are having the value with some error and the correct value, can you find the percentage error? Yes, sir, absolutely we can find. So what is the percentage error? See, this is now PL upon pi by 4 d square e, PL upon pi by 4 d square e is same only na in both of it. So can I cancel out? Yes, sir. So what is the percentage error? It will become 1 by 2 upon 1 by 2.25 upon 1 by 2 into 100. See what I did? Yeah. So what is the relative error? The difference between these two upon the actual value, upon the original value, original minus error upon original, isn't it? That is the way of finding the percentage error. So if you put all these values, this PL upon pi by 4 d square e, PL upon pi by 4 d square e is going to get cancelled out. Do you agree or not? Please answer me. Yes, sir, absolutely. Right. Right, so we'll left with this much value. So from here, what we are going to get? So the percentage error, if you calculate it, I assume that you are getting somewhere near 11.11%. Now, is it fine to you? Please answer me. Pradipta, you please also tell me. Did you understand it? Yes or no? Please answer me, Vida. Interesting, no? Yeah? Please answer me if it is fine or not. Do you want to try one more question? Hmm? Would you like to try one more? Tell me. Yeah, wonderful, Vida. See, these kind of questions you might not see in NCERT, right? So these are very good questions, right? Not the see. Normally, I have seen like the questions they are very easy, right away formula based. So we have done those. So we are trying to infuse more of the concept. See, you are using the same formula, no other formula. So let's do one more question. Let's see if this is clear to you. So see, what we, if you understand this, if diameter is varying uniformly, how to deal with it, we have understood. If the Young's modulus is varying, how to deal with it, that is also we have understood, isn't it? Now please try. Yeah, this one. Please try this one. After this, I'll move to one more concept. Okay. Please try answering. Please try. Very simple. Yeah, wonderful, Kunal. So it seems that you have understood the answer, na? Understood the concept. So we can move. So two tapering bars of the same material are subjected to a tensile load P. The length of both the bars are the same. The larger diameter of the each of the bar is D. Okay, larger diameter being D, right? And the diameter of the bar A of the smaller end. So let's suppose this is bar A. The smaller end is D by 2, right? The smaller end is D by 2, and that of the bar B is D by 3. Okay, that of the bar B is D by 3. Okay, so this is D by 3 and this is D. This is D by 3 and this is D. Okay, so what is the ratio of elongation? So see, what is the ratio of elongation of A by B? So what is the ratio of elongation? It is PL, length is same, pi by 4, D, D by 2 into E, right? This is for A. Upon for B, the same load is applying PL upon pi by 4, D into D by 3, D into D by 3 into E. So rest is cancelled out. We're left with 2 by 3. Okay. Right. So the answer is B option. I hope it is clear to everyone. Right. Please answer me. Yeah. Okay. Please give me yes or no. Right. Easy, no? So let's now move up with the concept. Okay. Now let's say that we have to find the elongation due to self weight. Okay, so see, these load what we call as the axial load. Now there can be self weight also in a body, isn't it? Any material has some weight density, so it has some self weight. Do you agree, Kumar and Pradipta? Yes or no? Please answer me. Every body has some self weight, right? Now we are interested in finding out that what is the elongation due to self weight, right? Okay, so how can we do it? Now you have to do it. You have to try to. So this is what you see as a question in your NCRT. Now I'll make a concept out of it. So let's suppose that this is a body. So normally they give you in terms of mg. I'll give you in terms of gamma. So let's suppose the gamma is the weight density. Gamma is the weight density, and it is in kilonewton per meter cube. The unit is kilonewton per meter cube. The length of this is L. Okay, area being A, and now you need to give me the elongation of this bar due to self weight. Can you please try it? Yeah, E is the Young's modulus. E being the Young's modulus. Can you please try? Let's see if we can do. So you do it. I'll just get some water for me, huh? Just give me 2 minutes. Kumar, fine, na? I'll just come and get me water till you attempt it. See, I'll give you one hint also. So if at all you have to consider x, you always consider the x from the free end. Okay, you always consider the x from the free end. Okay, please try. come on, no. Acha, into R into. It is into, na? Wonderful. See how we can do it. Now see, again we are having only one formula. Delta is equal to PL upon A. Right? Right? Yes, sir, absolutely. We are having only one formula. That is delta is equal to PL upon A. But here now you see, since the weight density is there, so what is the weight density? Weight density, now if I assume a section X, now let's understand this. So if I assume a section X, okay, yeah, understood, it is into, it is good only, it is correct. So if this is X now, if this is X now, now you see the load at X will be how much? Sir, it will be, see, in weight density, what I need to multiply to become a kilonewton? Because we require the load to be in Newton or kilonewton, right? We are assuming or we must have the load into Newton and kilonewton. This is the usual units that we deal with. Okay, we don't want it in terms of kilonewton per meter cube. Now, what shall I multiply? I shall multiply gamma into A into X. Yes or no? Shall I? I shall multiply gamma into A into X. That is weight density into volume. Okay. Now you see that X here is varying from 0 to L. Isn't it? When X is varying from 0 to L, this P is varying. Isn't it? See, what I am trying to do, I hope you are now getting that. So in the first case, I have varied the Young's modulus. In the second case, I have varied the area. Now in this case, I am varying the load itself. Right? Now when the load is varying or anything in variation, what we have to do? We have to write for a strip, we have to take a strip. So let us take a strip here. Now if I take a strip here, now if we take a strip here, so this is your strip now. Now this is your strip. Now on the strip if I write, the load is gamma into A into X, the length of the strip upon area into Young's modulus. So delta of strip will become gamma x upon E dx, gamma x upon E dx. Now if I integrate this equation, I'll be getting the delta due to self weight, and this will become, so if I integrate between 0 to L, gamma x dx upon E, so this will become, self weight will become gamma L square by 2E. Is it fine, beta? Please answer me. This is elongation due to self weight. Do you agree or not? Please answer me. Fine, na? Fine, na? Now see, from this equation, from this equation, elongation due to self weight is gamma L square by 2E. Okay. Now from here, can I say that delta, that is elongation for self weight, is independent, is independent independent of elongation of self weight is independent of diameter or area, isn't it? Can we say so? Can we say so? And proportional to L square, and proportional to L square, right? So the elongation due to self weight is proportional to L square and independent of area. But sir, we see one more formula. First of all, you tell me, is it fine up to this point or not? Now I'll show you one more formula, that how you see it and where is the confusion and how you get the confusion. Can you please answer it? Is it fine up to this point? Please answer me. Give me something if it is fine or not. Yeah. Fine only. Wonderful. Wonderful. Now see. I'll tell you something. So see what happens when you see this. There is one more way to seeing it. Let's suppose this is your bar, a prismatic bar, and now it is having the weight density of gamma. So when it is having the weight density of gamma, it is kilonewton per meter cube. It is kilonewton per meter cube. Now please understand this. So if I say this is x, if I say this is x and this is also x, okay. Now you understand this that if I write the load on this section x, it will become gamma ax. And if this is L, so the self weight will be maximum at the fixed end and it will become gamma AL, right? Isn't it? Now see, sometimes what they do, they say the self weight is, let's suppose P. The self weight is P or W. Let's write it W also. Normally they show you with W. Okay, so let's say they say self weight is W kilonewton. So when they say the self weight is W kilonewton, certainly it is not the density, because if it would have been the density, it must be per unit volume, right? Right? Tell me. It must be then per unit volume. Now, since it is not given as per unit volume, what will you refer it as? Like what will be the self weight? At what point self weight it would be there? So you will consider it the maximum self weight. That is self weight at the fixed end. That is self weight at the fixed end. Understood? That is the self weight at the fixed end. So W at the fixed end, it will become gamma AL. Okay, that is at the length. Now we just have sorted out this formula, that is delta of self weight is equal to gamma L square by 2E. Now from here, can I write that the delta self weight is equal to gamma is W upon AL, W upon AL, L square by 2E. W upon AL, L square by 2E. So it will become how much? See, it will become WL upon 2AE. Right? WL upon 2AE. Getting my point, beta? Getting my point. Now here remember that W is the self weight, that is gamma AL. So you might have seen this formula this way, or you might have seen this formula as this way. So sir, weight is mg. If the mass of the rod is given, you see it like this, mg L upon 2AE. Yes or no? Okay. Yes or no? Now, many students, when they see, when I say this, that the self weight is independent of the diameter or area, many students quote me this formula. That's this is also one formula. Na? In this, the area is getting divided. So, how it is independent of area? So, see, it is independent of area because this W is not a constant here. This W is not the external load here. It is due to self weight. So, it is varying. So when area, when you put W is equal to gamma AL, the A and A will be cancelled out and you are going to get the very same formula, the previous one. So when you are interpreting the relation, you always must use this formula, right? See, it is common sense. How? So one more formula, W L upon 2AE. Now from here you can say that the deflection is proportional to L and inversely proportional to area. So why can't we say so? Why can't we say so, my dear? So we cannot say so because here W is not constant, right? If at all the W would have been constant, then we would have said this. But here when W is not the constant, we cannot relate that deflection with length and area, right? But in the first equation, since the E is constant, okay, we can definitely relate it. Understood? So see, in what condition which formula to be used? This formula is to be used only. This formula is to be used only when the self weight is given in the unit of kilonewton. Is that fine, beta? Please answer me. Can you please answer me on this? Kumar and other students also. Can you please answer me on this? Is it fine to you? Yes or no? Yeah? Clear? Yes or no? Please answer me something. Now, see, one interesting thing is also here. So now, if see, now please understand this. So there is a comparison. There is a comparison. Now, if the self weight is W, W is the self weight in kilonewton. Okay. So now the elongation due to this self weight is half WL upon A is half W upon WL upon A. Now this WL upon A, do you believe that if on the same bar, if on the same bar this W self weight, if on the same bar, if this W self weight would be applied like this, like an axial load, if for the same bar this W is applied as the axial load, it is going to have a elongation of WL upon A, right? So now can I relate the self weight elongation with the axial load elongation, right? Isn't it? So the elongation due to self weight is half the elongation of the axial load if the same self weight is applied as an axial load on the same bar. Understood? Please answer me. Yeah, right. Is it clear or not? Please answer me. Please give me yes or no, my dear. Right? Fine. Now I want to ask you something. Let's suppose there is a bar. I'll like make one question. A bar having a self weight of 200 kilonewton is subjected to a tensile load of 100 kilonewton. Tensile load of 100 kilonewton. Okay, so एक बार है whose self weight is 200 kilonewton, and furthermore a tensile load of 100 kilonewton is applied on it. Okay, applied on it. Okay, okay. Find the elongation. Find the elongation of the bar. Find the elongation of the bar. We need to find the elongation of the bar. Okay, for length being 2 meter. Okay, area being 100 square, and Young's modulus being 100 GPa. Please go for it. Let's see if we can do it or not. Please try it. So there is a bar, it is having the self weight also, and some axial load, that is tensile load, is also applied. Right? Now you may please try it. Please try it. Kumar, are you trying it, Bida? See, all the new students to the channel, I request you to subscribe the channel, please, if you haven't yet. Please try. Let's try. I'm very sure we can do. Please go for it. Please go for it. I'm quite sure we can do. Please try. Please try, guys. Any answers? Please try answering it, my dear. Let's see how we can answer. Any answers? Please do. Let's see how we can do it. Please do it. So see how we can do it. So it says a bar having a self weight of 200 kilonewton is subjected to a tensile load of 100 kilonewton. Find the elongation of the bar for length is equal to 2 meter, area is equal to 100 mm square, and Young's modulus is equal to 100 GPa. Okay. So how we can do it? So there is a bar. If nothing is mentioned, you always assume the bar of uniform cross section. Okay. You always assume the bar of Pan, a very good afternoon, my dear. So we are trying to understand the properties of the bulk solids in this class. My name is Dr. Shankar Sir. How are you doing, Bida? Shall you try this? Do you want to try this question? Do you know about the self weight? case. Yeah. Please answer it if you want to. Are you attempting it, Bida? Okay, so I shall do it. Now see, what does this question say? So we are having a bar. Let's suppose the self weight of this bar. So what is the self weight given? The self weight of this bar is given as 200 kilonewton. The self weight mentioned is 200 kilonewton, and the tensile load on this bar is 100 kilonewton. The tensile load on this bar is 100 kilonewton. Find the elongation of the bar. So let's suppose L is 2 meter. Okay, L is 2 meter. Okay, and area is 100 mm square. Okay, this is given. So now see, in this case, see, in this particular part of physics, there is one very important concept, that is superposition theorem. That is what? Superposition. Like, what is the superposition? So here we are having an axial load also. We are having a self weight also. Now you need to give the elongation, right? So how you can do it? So when you have to give the elongation, see what you can do. So see, here there are two effects. There is net elongation. What is the net elongation? The elongation due to the axial load. The elongation due to the axial load, okay, and the elongation due to the self weight. Elongation due to the self weight. Are you getting my point? There are two things in this. So see, we have to add their individual effects. Okay, so when we are having a delta, when we are having a delta, okay, so see, we have self weight also, we have axial outside load also, right? So what you have to do when you are finding the net elongation or the total elongation of this, so what you need to do, so you need to add both their individual effects. So what is the elongation due to axial load? So this is going to be 100, that is 100 into 10 to the power 3 into L, that is 2000 upon area. Area is 100 and E is 200 GPa. So 200 into 10 to the power 3. I can change it to megapascal because 1 megapascal and 1 Newton per mm square are the same thing. Uh, Janitha, a very good afternoon. Okay. So now, what is the elongation due to self weight? So self weight is 200. So it is 200 into 10 to the power 3 into L, that is 2000 upon area into Young's modulus 200 into 10 to the power 3, isn't it? Right? But sir, one thing is there, that we have to divide it by 2 also. Because see what we have learned. So for self weight, it is WL upon 2A, and for axial load, it is WL upon A. Right? When both are acting, you have to add their individual effects. Right? Now, if you do some calculation, you will be able to get it. See what we are getting. So see, due to axial, so 100 is gone, this is gone, so this is going to be 10 mm plus this is gone. Okay, this is 20 by 10, 2, that is 10. So it is going to become 20 mm. Are you getting my point, Buddha? Okay, 20 mm the net elongation here. So see, simply what is the conclusion? So when both self weight and axial load, that is the outside load, acting simultaneously on a body, what you can do? When both when both when both axial load and the when both axial load and the self weight both acting simultaneously on a body, or you need to find the elongation due to both of their effects. What you can do, you can individually find the deflections of theirs and then add them up, right? Right? Understood, my dear? Please answer me. Is it fine to you? Yeah, this is what we know as the superposition, right? Any issue? Please answer me. Any issue, my dear? Is it fine to you? Is it fine to you guys? Yeah, the live students, please tell me. So now individually, see what point we have reached. So till what point we have reached. So individually, if a load is acting on a body, outside load, a deformative load, if a outside axial load, tensile, compressive, anything like that, if acting on a body, will you be able to find the elongation due to that? Yes, sir, certainly. Now, if a self weight is acting on a body, will you be able to find the elongation due to self weight? Yes, sir, certainly. If both, if both self weight and axial load is acting on a body, will you be able to do it? Yes, sir. Will take their effects, will calculate their deflections individually, and then we further add them. Firstly, we are going to calculate their elongations considering them acting on the very body separately, and then after we'll add both of it and we'll get the answer. Fine. Okay. Now let us see. So now if I ask you, let's suppose that we are having a conical bar. Okay, let's complicate. See, when you know the concept, nothing is complicated, right? Okay, so we are having it like this. Let's suppose we are having a conical bar. Now you need to find the elongation of this conical bar, elongation of conical bar due to self weight. Okay. Now again, I am assuming that the weight density is gamma, and again it is kilonewton per meter cube. Now you need to give me the weight. Acha, just one thing. If you want to find the stress in this case, so what is going to be the stress at x? So obviously it is the load upon area. So gamma ax upon area. So stress, if you have to find, it will become gamma x. It will become gamma x, right? In the self weight case. Okay, now let's try it. You please give me the elongation. You please give me the elongation. Please go ahead. I'm very sure we can do. Please do. Let's try to do it. I'm very sure we can do. Please go ahead and try to solve it. Very important concept. Please try to do it. Please try it. Please answer it. I'm very sure we can do. Please go ahead. So see sir, again you have to do it very simply in the same manner you must try. See how we can try it. Now see, we are having this conical bar. So when we are having this conical bar, what we can assume? What we can assume? So we can assume this is, let's suppose x, this is L, right? The same way, same approach we can do. And the self weight is gamma kilonewton per meter cube. So can we write the load at x? So sir, it is gamma into volume. What is the volume? 1 by 3 area into length. Okay. 1 by 3 area into x, right? Now remember, see, why is it 1 by 3? Array, for conical, cone area is 1 by 3. Sorry, 1 by 3 pi by 4 d square into h na. So Harsh, hello, very good afternoon, Jai Shri Krishna. How you are doing? Long time. Right. So Px is equal to gamma Ax by 3. Right. So now what we can do? So we can again go for, so see here area is the section, area of section x. So I'll write it AXX. Now what is going to be the elongation of the strip? So how we can write it? It is going to be Pxx dx upon A. Again, we have only one formula, remember. Right, so what is this Pxx? This is going to become gamma Ax by 3 dx upon A. Right. Harsh, there might be some technical issue. थोड़ा कुछ technical issue रहता होगा. Maybe due to that reason. Okay. Are you coming in the sessions? Anyways. Okay. So now we can do like this. So we are having gamma Ax upon E. So now we can integrate gamma x upon 3e dx. Right? So now when we are integrating it, this will be gamma L square by 6e. Right? Okay, because when we are integrating between 0 to delta, okay, 0 to delta, so this is the elongation of conical bar due to the self weight. Okay, so this is what we call as the self weight case and the for the conical bar, right? So it will become gamma L square by 6e. See, when we are going to see the strain energy now, it is, these all points are going to be clear for you. So normally this conical bar, so see, when you know the concept, be it uniform diameter bar, be it conical bar, be it anything, you will be able to understand that. Okay. So Harsh, what we did today in this session, I just give you a brief. See, you might be aware of this formula, right? See, we are into the properties of solid. Okay. So see, we have only one formula to use, that is delta is equal to PL upon A, isn't it? So whenever we want to find the elongation, we have only this formula, that is delta is equal to PL upon A, right? Delta is equal to PL upon A. Now see, if you see in this question, so what I tried to do in this session, see, I wanted you guys to understand that in what conditions you can use this formula, and there can be, different use cases of this formula. And remember, we have only this formula. Like in this question, we are having the Young's modulus as 100 e to the power minus x. Okay, 100 e to the power minus x GPA, right? So here the Young's modulus in this question is varying. So what we tried to do, we tried to put it into the formula, and what I tried to infuse into you is that whenever we are having whenever we are having anything varying in this formula, we can always integrate. So in this, see, we put everything, we integrated, we got it. Then we have seen the tapered bar case, right? So here the diameter is varying, so we have again integrated and found this formula, the elongation of a tapered bar due to some load. Then we started with so we have solved some question on it, so you can always see the session again, right? Oh, the light is gone. Oh my goodness. Okay, anyway, so just some power cut happened. Okay, anyway, so you have to see me a little blurry for few minutes. I hope it is fine to you. Well, I just switch off the video for a moment. Right? See, sometimes some things are not in my control. Okay, so anyway, it is fine. It is looking fine only, right? Isn't it? Yeah, it is fine only. I am looking beautiful. So see, now see. So delta is equal to PL upon A. Now in this case, self-weight, again see, in the self-weight case, the load is varying. When the load is varying, we can put everything in the formula and then we can solve it, right? So when we put everything into the formula, we'll get something like this, right? Gamma L square by 2E. Then we solve some questions of it. We have, we have somewhat integrated it, both the cases, the axial load one, the self-weight one, and we have seen that what is going to happen, like in this case. And now we have sorted out, we have sorted out this one also, right? We have sorted out this one also. I hope it is clear for the conical bar, Harsh and every new student. Please answer me. Yeah. Understood. Okay. Now let me tell you one more beautiful concept. Okay. No, let's first do one question. So let us suppose we are having something like this. We are having a frictionless pulley, right? You must have seen all this in Newton's law. And there is a string attached to it. Like this. let's suppose this is 2 kg, this is 4 kg. Just make it a little bit better. Suppose this is 2 kg weight, this is 4 kg weight. You must have seen in the Newton's law, right? And let's suppose this is attached, the police attached to this like this, and we are having, so this is a wire. Sorry, this is the wire, right? And the breaking stress of the wire is breaking stress of wire. It is, let's suppose, breaking stress of the wire is suppose 2 into 10 to the power 5, that is 200 megapascal. Okay, and you have to find the minimum cross sectional area, minimum cross sectional area of wire, minimum cross sectional area of wire. Please write minimum cross sectional area of the wire. Okay, please do. I'll give you some options here. So we are having 2.66. All the answers in centimeter square. So 2.66 centimeter square, 1.66 centimeter square. We are having 3.33 centimeter square, and we are having 1.33 centimeter square. Can you please try it? I'm very sure we can do. Please go ahead. Please go ahead and try to solve it. Please try, the live students. Please try it. I'm very sure we can do. Can you please do? Please do, guys. I'm very sure we can do. Any answers? Very simple question. Any answers, guys? Please try answering it. See, I'm very sure we can do it. Please go for it. The live student can respond to me. ओके, तो देखिए कैसे कर सकते हैं, हाउ कैन वी डू इट. So now see, due to this 4 kg, so the motion of this mass will be in downward, the acceleration of this mass will be in downward direction, isn't it? Now since the acceleration of this is in downward direction, there will be a tension here, okay? And the force of mass into acceleration always acts opposite to the acceleration. So from here I can write one equilibrium. What is it? So I can see that T plus 4A is equal to how much the weight, that is 4G, isn't it? Let's suppose this is equation number 1. Let us suppose this is equation number 1, isn't it? Yeah, right? And now if I write the equilibrium for the 2 kg mass, right? The acceleration of it will be in upward direction, so MA will, for this MA will be in downward. So can we write and tension will be like this, right? Tension is like this, okay? So we can write here, so T, yeah, let's try it. So there was some technical issue. I hope it is sorted now. Yeah, just one moment. Sometimes some technical issue do happens. Okay, so I was speaking of this question. We were solving this question here, right? We were solving this question, just a moment. So I'll just sort it out. Just a moment, guys. Huh? Yeah, so we have been doing this question, guys. Okay, can you please try to answer this question? Let's see if we can do it. Can you please try to answer this question? I'm very sure we can do it. Please go ahead. Let's see if we can do it or not. Yeah. Okay. So I was speaking of this question. Guys. So see, there was some technical issue. That is why it was lagged. Okay. Now I have written the equilibrium of this 4 kg mass. Okay. So what is the equilibrium? So see, T acts in the upward direction opposite to the direction of the load, and since this will accelerate it in the downward direction, the MA will act upwards. Okay, so the mass of this weight is 4. So we have written it T plus MA, that is 4A, is equal to 4G. Okay, now if we see this 2 kg part, if I write the equilibrium for it, it will become, see, the tension will be in upward direction. This is going to be your tension. So T minus 2A, see, T, so plus 2A in this case, okay, T plus, you see, 2A in this case, Okay, no, so just a moment. So see, this is the mg is acting downwards. So I may write mg, that is 2g, and the acceleration of it will be upwards. So it will be a will be ma will be downwards. So it is going to be minus of 2 times acceleration. Minus of 2 times acceleration. This is going to be 0. This is going to be 0. Right? So it will become t minus 2a is equal to 2g. Let's suppose this is equation 1. Now from here, can we calculate this t? Can we calculate this t from here? Isn't it? Right? So now let's calculate the t. So if I multiply 2 here and subtract with this equation, so what I'm going to do? See, I'm just simply solving this equation number 1 and 2. So if I multiply 3 in equation number 2 in equation number 2, so it will become, and add it with equation number 1, so it will become 3t a, and this will become 8 times g. So t is equal to 8g by 3. This is going to be the tension in the wire, right? This is going to be the tension in the wire. Now you come to know the load in the wire. You ultimately come to know the load in the wire. So now when you know the load in the wire, what will be the area, minimum cross section area? So in the last section we have understood a concept. What concept? That the induced stress on any body must be less than equal to is breaking stress, isn't it? It must be less than or equal to the breaking stress. So what is the induced stress? It is force upon area, that is T upon A, and the breaking stress is 200 megapascal. So that is 2 into 10 to the power 5 Newton per meter square. So this is 8 G by 3. So G I have put 10. This is A, and this is less than equal to 2 into 10 to the power 5. So from A here we can get the A. So A is greater than equal to, A shall be greater than equal to 8 into 10 by 3, okay, into 2 into 10 to the power 5, and this will be in meter square. So I want to convert it into centimeter square. So I'll multiply 10 to the power 4, and this will become centimeter square. So see, this is gone, and it will be 8 by 6, greater than equal to 8 by 6. So this is somewhere near 1.33 centimeter square. Okay, so for you to be saved, for your wire to be saved under this condition, the area should be 1.33. The minimum area should be 1.33 square. So it must be your D option. Is it fine, my dear? Please answer me. Yeah, any issue? Any issue? Okay, wonderful. Wonderful. Now we have one more question if you want to try it. Easy, sir. I like all 3 subjects of NEET. I want to study deep in all. So, as I said, beta, see, who is stopping you to study those? Why are you not studying them? See, as I always say, na, see, I can give you only recommendations, the suggestions as per my experience. Okay? Nobody is stopping you from studying them deep. You please study them deep. Right? See, with the things that you are telling me, so it seems to me that you are more interested in gaining the knowledge in the subject rather than, qualifying the competition, right? So basically what happens if you do like that, it will be very hard for you to qualify the competition. So what I suggest, if you're more interested towards studying of the subject in deep, why don't you choose BSc, MSc and PhD? You leave the NEET. Na? What is, see, NEET is not the only career that one can have, right? See, I was interested towards studying deep into this physics. Okay, I did masters, then I did PhD. Why you are not following that way? What is the problem? Who is stopping you? Who is stopping you doing that? Hmm? Anyone? Is it stopping you doing that? Please answer me. So that is, see, how can I comment on that, my dear? Right? Okay. So you have to talk to him, right? See, there is a great career ahead in that field. Even better, I have made one video on the channel in which I have given that there are more, there are some more career options other than the NEET, right? Have you watched that video? In that video, I have told something about the research institute in India. See, this way, if you are approaching, you can't crack NEET. Are you getting my point? See, let me tell you the fact, my dear. See, from my experience, you can be an exception, right? I mean, I may get wrong. But see, for competitive study, you have to be very concise that what you are studying, my dear. If you study all the things in the world in one subject, you will not be able to crack the competition because see, you have so many subjects to deal with, and in competitive examination, you have to filter out the information. This is not your board exam or any, semester exam. Okay, this is the first thing. See, try to understand this. Uh, Okay. Now, second point is like you are saying, sir, you are, see, many times we have had this conversation. So you are saying that, sir, you are interested in studying deep of the subject. Okay. So there is no problem at all. If you want to study neat, if you want to study deep in any subject, what I prefer you, one good career option is you go into the research field, right? You do BSc from some good college, right? In any of this, physics, if you want to pursue chemistry, biology, whatever you want to pursue, you do BSc. What is wrong with it? Nothing is wrong. After BSc, you can do MSc, right? Or there are some IITs, IIT Madras, and all. They are offering integrated BSc MSc program. It is not possible now, right? See, I am telling you frankly that this is very hard for you. If you are trying deep also, so that is what I suggested you previously. The same thing what your father is saying. That once you crack the need, then do anything that you want. Na? This is what I said. But if you are like, see, if you are, if you are trying to cross the boat, sitting in two boats together, you can't cross the river sitting in two boats at a time. It's as simple as that. And my plain suggestion to you on this, either you choose one side. If you want to crack the NEET examination, you have to study just sufficient. If you keep on studying more than that is required for this competition or any competition that you are going to give in future, or any student who is going to give in future, right? It is not going to work for you, my dear. It is not at all going to work for you. Are you getting my point? Okay. Okay. So this is my suggestion to you. It is up to you to, um, uh, believe it or not, or follow it or not, right? You please try it before. So for NEET examination, you have to be concise. You have to be, according to me, you have to be uh, studying concisely, right? Okay. So let's do one question. So let's suppose we are having a, you know a string with us. We are having a string with us of some length L, okay, of some length L and area A, okay, and it is having some mass attached to it, okay, some mass, something is mass there. अच्छा ठीक है. हाँ, ये भी नीट करने के बाद भाई डिटेल में पढ़ो ना यार, है ना? और अगर अभी भी आपको पढ़ना है यार, तो फादर को समझाओ यार, क्या है वो तारे जमीन पे दिखाओ उनको. आर यू गेटिंग माई पॉइंट? ठीक है, उनको 2 दिन बिठाओ, तारे जमीन पे दिखाओ, 3 इडियट दिखाओ, समझ जाएंगे. समझ गए? ठीक है कि भैया मुझे बीएससी करना है, करो बीएससी यार, कौन रोक रहा है ना? वो जमाना थोड़ी ना है. आर यू गेटिंग माई पॉइंट? वैसे पेरेंट्स हमारे लिए अच्छा ही सोचते हैं, ऐसी बात नहीं कह रहा हूँ कि मतलब जा करके वहाँ पे तहलका मचा देना, आंदोलन कर देना, ठीक है, लेकिन दिखाओ यार एक आध पिक्चर, अगर ऐसी बात है तो कोई क्या होगी बात, है नहीं? समझ रहे हो कि नहीं पापा मुझे तो फिजिक्स पढ़नी है, बीएससी करना है, एमएससी करना है, नेट करना है, पीएचडी करना है, विदेश जाना है, रिसर्च पेपर लिखना है, समझ जाएंगे, है ना? बोलो, कह दो एक मास्टर सामने का है, मेरा वीडियो दिखा देना, ठीक है? कोई दिक्कत नहीं, जरूरी थोड़ी ना हर आदमी डॉक्टर ही बन जाएगा, कुछ लोग रिसर्च भी करेगा ना, वही दुनिया में। क्यों कि हर आदमी लेकर डॉक्टरी करेगा? जब सब कोई डॉक्टरी करेगा तो डॉक्टरी करने वाला इंस्ट्रूमेंट कौन बनाएगा? टेक्नोलॉजी कौन बनाएगा भाई? है ना? समझ रहे हो? हर किसी चीज़ की इंपॉर्टेंस होती है, ठीक है? हर किसी चीज़ की इंपॉर्टेंस होती है। रिसर्च अपने आप में बहुत इंपॉर्टेंट है और उसका कैरियर इससे ज़्यादा अच्छा है अगर आप अच्छे से करें वो काम। तो अच्छे से आप नीट निकाल करके अच्छे से ना करिए, एम्स में एडमिशन हो गया बता, तो पास ही नहीं कर पा रहे हैं, एमबीबीएस ही नहीं कर पा रहे हैं, एमबीबीएस की उसके एमडी नहीं कर पा रहे हैं, तो क्या होगा? कोई फायदा नहीं होगा। आर यू गेटिंग माई पॉइंट बेटा? ठीक है, तो जो मन में है वो करिए, क्या बात हो गई? और अगर नीट करना है तो फिर बेकार में इधर उधर दिमाग मत लगाइए, फिर जो पढ़ाया जा रहा है वो पढ़ लीजिए, खत्म करिए, ठीक है? बहुत ज़्यादा इधर उधर सोचेंगे कि लो सर ये बुक भी उठा लाऊं और वो बुक भी उठा लाऊं, तो ऐसे मत करिए वरना नहीं होने वाला, ठीक है? प्लेनली मैं बता रहा हूँ, आप समझिए बात को। आपके हित के लिए ही बोल रहा हूँ, बाकी मेरा क्या हित है यार, आप जाइए पढ़िए भाई, मुझे कोई डाउट आएगा मैं आपसे पूछूंगा, ठीक है ना? लेकिन समझो कुछ कंपटीशन ऐसे नहीं होता है, ठीक है? इतना लोग कंपटीशन ले रहा है, कितना लोग देता है कंपटीशन नीट का बताइए? हाउ मेनी स्टूडेंट्स आर प्रिपेयरिंग फॉर द नीट एग्जामिनेशन? बोलिए, हैव यू गिवन एनी मॉक टेस्ट? हाँ हाँ, तो करो ना एमबीबीएस, क्या दिक्कत आ रही है? मतलब एमबीबीएस भाई एक बार बताओ, नीट में नहीं होगा तो आपके फादर के चाहने से हो जाएगा? बताइए कि नहीं एमबीबीएस करिए। नीट में नहीं हुआ तो क्या है फिर भाई, किसी प्राइवेट कॉलेज में करोड़ों रुपए का डोनेशन देंगे और फिर लोग एडमिशन। वैसा चाह रहे हो तो क्या दिक्कत है? अगर वो एक एक डायरेक्शन होती है, दूसरी डायरेक्शन क्या है? भैया नीट 22 लाख लोग दे रहा है यार, 50,000 सीटें हैं, समझ रहे हो? किसी के चाहने से मैं चाहता हूँ कि आपका नीट है, आप एम्स में चले जाओ, मेरे चाहने से, आपके चाहने से, आपके फादर के चाहने से, किसी के चाहने से हो पाएगा? जब तक आप मेहनत नहीं करेंगे, नीट में नंबर नहीं लाएंगे। बोलिए, ये तो आप मुझे बोल रहे हैं, खुद को बोल रहे हैं, फादर को बोल सकते हैं कि नहीं भाई माई फादर वॉन्ट्स मी टू go into MBBS. But without the NEET score, no matter how many, every father wants his son to be, son or daughter, okay, to be in a good college, to pursue a good career. But just by that, things do not happen that way, right? So, anyways, let's continue. So, let's suppose we are having a pendulum. We are having a pendulum like this. Okay, this is some sort of a pendulum, and its length is L, A is the area of it, and let's suppose T is the time period of oscillation. T is the time period of the oscillation. Okay, T is the time period of oscillation. Right, T is the time period of oscillation. Okay, so this data is given. Now, in this, let's suppose a mass capital M, okay, is attached with the bob, is attached with the bob, okay, ठीक है? तो टाइम पीरियड ऑफ ऑसिलेशन आपको आता है ना? हमने पहले भी बात की थी, आपने चैप्टर भी पढ़ा होगा। अगर नहीं पढ़ा है तो भी कोई बात नहीं है, मैं अभी फॉर्मूला बता दूंगा, आप निकाल लीजिएगा। तो अ मास m इज अटैच विद द बॉब and the time period of oscillation then is the time period of oscillation, the time period of oscillation then is tm, ठीक है? then is tm, right? अब आपको क्या बताना है? आपको बताना है what is the ratio of 1 by e, okay? फाइन 1 by e क्या है? यंग्स मॉडुलस है, ठीक है? आपको 1 by e निकालना है इसमें। आर यू गेटिंग माय पॉइंट? e क्या है? ये है यंग्स मॉडुलस, मॉडुलस ऑफ इलास्टिसिटी। ओके, सो आई विल जस्ट गिव यू सम ऑप्शंस। Let's try this question. I'm very sure we can do it. करेंगे, कोशिश करेंगे बेटा. चलिए, let's try this one. करिए, कोशिश करिए बेटा. इसको सॉल्व करेंगे. I'm very sure we can do. करिए, कोशिश करिए. Very interesting question. Please try to solve this question. I'm very sure we can do it. Please do it, beta. All the live students. Please do, guys. Okay, I'm waiting on you. Please go for it. I'm very sure we can do. Please do. हाँ, बहुत अच्छी बात है ये। हाँ तो बेटा वो सही बोलते हैं ना, गलत क्या बोलते हैं बताइए, क्या गलत बोलते हैं भाई? मतलब मैं भी यही बोल रहा हूँ कि नीट के बाद पढ़ लेना, है ना, लेकिन मैं ये भी बोल रहा हूँ कि अगर आपका नहीं मन है यार तो मत पढ़ो ना यार, क्या बात हो गई। लेकिन ये आपके और उनके बीच का मैटर है भाई, इसमें मैं क्या कर सकता हूँ बताओ आप, है ना? अरे मीटिंग माई पॉइंट माई फ्रेंड। सो बेसिकली मैं आपको सजेस्ट कर सकता हूँ, अगर आप नीट को लेकर के सीरियस हैं और रियली उसको करना चाहते हैं तो आप बहुत इधर उधर डाइवर्ज मत करिए। आप सीधे रास्ते चलिए कि ठीक है भैया, हमको सब्जेक्ट कंप्लीट करना है मेरे को, है ना, और सब्जेक्ट कंप्लीट करके मुझे भैया नीट निकालना है, सारे सब्जेक्ट कंप्लीट करूंगा, पीवाईक्यू करूंगा, मॉक टेस्ट करूंगा, ये करूंगा। उसको काम के लिए आपको किसी भी सब्जेक्ट में बहुत डीप में पढ़ने की जरूरत नहीं है। ठीक है, बताइए। अच्छा चलिए मुझे ये बताइए कि फिजिक्स में कौन सा टॉपिक आपने डीप में पढ़ा है? चलिए लेट्स नॉट गेट इनटू दैट। ओके, please solve this question. So you are saying that you have studied physics in deep. So can we solve this question, please? Let's see. Let's try to solve it. Please try it. कोई बात। तो बेटा ये चैप्टर नहीं पढ़ा तो ये सेशन शुरुआत से क्यों नहीं देख रहे हो? तो समझ जाओगे सारी चीजें। नहीं, क्यों कंफ्यूज हो, यही तो मैं पूछ रहा हूँ आपसे। वही आर यू कंफ्यूज? नहीं तो कंफ्यूजन को दूर करो ना मेरे भाई, क्यों कंफ्यूज हो? वाई यू आर कंफ्यूज? See, when you want to study a subject deeply, there is no problem in that, provided that when you are studying that subject deeply, your preparation of any competitive examination must not suffer. If due to that your competitive study is suffering, so that means, yeah, okay, okay, I'm waiting. No, you please solve the question. See, students here are trying to solve the question. You can also try, isn't it? हाँ तो ज़्यादा डीप यार, इसी वजह से तो लोग मना करते हैं कि बहुत डीप में भैया किसी कॉम्पिटिटिव एग्जाम के लिए तैयारी नहीं किया करो। तो बहुत डीप में करोगे, कोर्स इतना है कहाँ से होगा? ठीक है, जादूगर थोड़ी है। ठीक है। हाँ अगर आप मान लो सुपर इंटेलिजेंट होते तब एक अलग बात थी, लेकिन आप समझिए कि आप मतलब या तो जीनियस टाइप के हो, ठीक है, हो भी सकते हैं आप, आई डोंट नो, है ना? लेकिन मतलब मेरे जैसे इंसान के लिए पॉसिबल नहीं है। देखो हर आदमी अपने तरीके की बात करता है। मैं मेरा जिस तरीके का दिमाग है, अगर मैं वही किसी कंपटीशन के लिए पढ़ रहा हूँ, ज़रूरत से ज़्यादा डेप्थ में पढ़ने लगूंगा तो कोर्स ख़त्म नहीं होगा, इस सिलेबस में दिक्कत आएगी। अंडरस्टैंड? दैट इज़ व्हाट माई approach is, and again my suggestion to you on this is that only. बताइए क्या बोलूँ मैं इसमें? But are you still trying the question or shall I solve it? Shall I solve it? Shall I solve it now? Okay, so let me solve it. So now in the first case, we are having a pendulum and a bob, and we are having to find the time period of oscillation. So now we know the relation that T is equal to 2 pi root over L by G. 2 pi root over L by G, right? T is equal to 2 pi root over L by G, and now see what it is saying. So this is in the first condition. Now in the second condition, the time period becomes Tm when a mass m is added to it. So when you add a mass to it, let's suppose you have added a mass capital M to it. Now due to this addition of mass, there will be some deflection of it. Okay, so the new time period will be L plus delta upon G. Do you agree to it or not? Please answer me. Yeah, absolutely, sir. Absolutely, isn't it? Right? Isn't it? Now, uh, if I write, so this is Tm. If I take the ratio, हाँ तो पढ़ो ना, उसके बाद पढ़ो, क्या दिक्कत आ रही है? चलो तो इन दोनों का रेशियो ले लिया. लेट्स टेक द रेशियो ऑफ इट. सो यहाँ दिस इज 2 पाई. Sorry, 2 pi. So 2 pi is cancelled out, and we are having Tm by T is equal to, so it will be root over L plus delta upon L. So it will become 1 upon delta by L, right? 1 upon delta by L, isn't it? Right? इन दोनों का रूट ले लिया, इन दोनों को मतलब रेशियो कर दिया. सो जब आपने इन दोनों का रेशियो किया, व्हेन यू हैव डन द रेशियो ऑफ दीज टू, so Tm by T, Tm ratio or Tm by T. So basically you have divided these two equations. So when you have divided this two equation, you will be getting root L by delta upon root L. Okay, root L by delta. Okay, okay. Okay, I'm waiting. No worries. You please solve the question. Yeah. देखो भाई, एक चीज तो आपको सोचनी ही पड़ेगी. समझ रहे हो भाई? वो बताओ, कुछ खाने में आपको पसंद है, जब वो चीज़ आप खाने जाते हो, बहुत पसंद है, आप बहुत पसंद है, लेकिन पेट भर गया. पेट भरने के बाद कितना ही खाओगे? बताओ. पसंद बहुत है, लेकिन पेट भर गया, तो उस समय भी तो खुद को कंट्रोल करते हो ना, कि नहीं करते हो? खा ही जाते हो पूरा. है? गए थे किसी होटल में पिज़्ज़ा खाने, पिज़्ज़ा इतना अच्छा लगा, सारा ही पिज़्ज़ा खा गए, कंट्रोल ही नहीं हुआ. इट मेक्स नो सेंस एक्चुअली. आर यू गेटिंग माई पॉइंट? ठीक है, इसकी सेंस नहीं बनती. तो इफ मीन वाइल यू कैन प्लीज सॉल्व द क्वेश्चन. There is no sense to it. To me, you can always control. How you can't control? Huh? How is this possible? Right? I want to teach you for 24 hours in a go, but my age, my body can't allow me to teach more than 4 hour 30 minutes, 5 hours in a stretch. How can I control myself to teach more? It is not controlling. This is the necessity. This is how things work. Right? Right? I want to control my sleep. Can you? So one day you can do, 2 day you can do. You can always exercise control on anything you want. Are you getting my point? Okay. So the remaining students, the new students who have come live to the session, so I please request you to subscribe the channel firstly. And in this session, what we are doing, so we are basically trying to solve questions we are dealing with. You see this uh, properties of solids, and we have done some Hooke's law concept, we have done some Poisson ratio concept, right? And we are now dealing with all these concepts to some extent. All right. Okay. So see, now I have taken the ratio of it, so it will goes like this. So can I write Tm by T whole of a square 1 plus delta by L? Can we write like this? So from here, can we write delta by L is equal to Tm by T whole of a square minus 1? Right, now what is this delta? What is this delta? So delta is force L upon area into Young's modulus. So this is L, this is going to be Tm by T. This is going to be Tm by T whole of a square minus 1. Tm by T whole of a square minus 1. So we can cancel this L out, and we wanted to have 1 by E. So it will become Tm by T whole of a square minus 1, Tm by T whole of a square minus 1, and it will become A upon mg. So let's see what option is matching. D option is matching. Is that clear, my dear? Please answer me yes or no. Uh-huh. So you are unable to see it, so I'll just write it small. A by mg. Right. So see, did I do anything new? Only the packing of the question has changed to some, extent. See, in physics, there is I always say in physics, there is a lot of scope to twist the, you know, question. They can give you multiple data. They can, use multiple concepts for you, or multiple things in a question for you to solve. Understood? Yeah. Is it fine? How we have done it? Right? Please answer me. Please answer me. Right? Now see you. What I'm trying to, so in today's session till now we have seen so many good, concepts. So initially, so how, see, till now what I, because see, most of the time we what we are seeing understanding the use of these expressions. Sigma is equal to P upon A, delta is equal to PL upon A, like longitudinal strain is change in length upon original length, and delta epsilon L is lateral strain is mu times longitudinal strain, that is delta L by L. Right, so all these concepts that we are seeing, and I am assuming here the load is applied in this direction like this. Okay, see, there are so many things. So we have, using these equations only, we have seen if Young's modulus is varying, how to deal with that. If the area or diameter is varying, how to deal with that. If the load is varying, how to deal with that. In conical bar, both load and area were varying, how to deal with that even. Right, so all this thing we have seen till now. बेटा आप सबसे पहले ना अपने माइंड को क्लियर करिए, किताबें सभी सही होती हैं, समझ लो, ऐसा कुछ नहीं है कि किताब में कोई कमी होती है या कोई किताब कम होती है, कोई किताब ज़्यादा होती है। आप पहले ये सोचो कि आपको करना क्या है, पहले आप उसको डिसाइड करो, ठीक है। आधा फिर उससे क्या है, भाई एक बार बताओ, एक बात समझिए, ठीक है। आपने मान लीजिए आज के दिन पढ़ा कोई सब्जेक्ट, ठीक है। अब आपका उस तरफ अप्रोच है नहीं, अब कल आप उसको पढ़ोगे नहीं, या कल उस डायरेक्शन में पढ़ोगे नहीं, तो जो आज पढ़ा वो भी बर्बाद होगा ना, वही यू आर वेस्टिंग योर टाइम। You first sort out that I have to do this or I have to do this. Then only anything can happen, right? Unless you sort this out, you will always be in trouble. Are you getting my point? Please try to understand. Okay, this is what I suggest you, that first you. So what you have decided? Are you going for NEET? If you are going for NEET, okay, let's not have this discussion any further in any further session also, because see, we have discussed it quite a few times, isn't it? The same thing. हाँ हाँ, so अभी सिर्फ relevant पढ़ो, that's all, matter is over, don't talk about it any further, right? So now when you are doing it, so you can please watch all the sessions and you try to, whatever topics you haven't done yet, you try to find good videos of it and you try to solve it or try to cover those topics. Okay. So see, properties of materials, I hopefully will be finishing in the next session. That is why I am having the big sessions, okay? Because few days I couldn't take classes, so I am now again, putting the gear the to it. हाँ हाँ, नीट के बाद कुछ भी पढ़ो यार, जो मर्जी हो पढ़ो, समझ रहे हो? ठीक है, कोई दिक्कत नहीं है उसमें, ठीक है? So after this, I'll be beginning with the fluid part and then the thermal part, right? Chalo, anyway, so we have understood the use. Now let's see one more question. Now we'll have having something like this. Let's suppose, and we are having two dots. Let's suppose we are having some two dots, okay, and a you know rigid bar is attached to the ends of this like this, and this is 2 meter. This is, let's suppose, 2 meter, and let's say that this is steel. This is steel, and its Young's modulus is. So are you able to see it? Okay, yeah. Its Young's modulus is 200 GPa. Right. Another material for it, be it copper. Okay, and for copper, it is 100 GPa. Okay, it is 100 GPa. Young's modulus of copper is 100 GPa. Right now, for what is asked, so now let's say that where should be, so on this we are putting some mass. Okay, let's suppose on this bar we are putting some mass to it, right, like this. So now we are putting some mass to it, like some m over here. So now when we are putting some mass m over here, what is going to be the, so see, where mass m, where mass m should be, where mass m should be, okay, where mass m kept, should be kept, so that so that in steel and copper, in steel and copper, in steel and copper, the stress is same. Okay. So what we need to find? So we are having two rods, one is steel, one is copper, and some mass is placed over this rigid bar, and they both are having the same length. Obviously, it is quite clear from the figure itself. And you need to tell me that for same mass, for same stress in both of it, what should be at from what should be this x? Let's suppose this is your x. What should be the x? You need to tell me that. Please go for it. I'm very sure we can do. Just write some options. Okay, let's do it. Let's try to solve this one. I'm very sure we can do it. Please go for it. Please do this, guys. I'm very sure we can do it. Any answer to the question? Can we please try it? I'm very sure we can do it. Please try, my dear. Please do. Okay, so how we can do it? So please do it. So see how we can deal with it. So see, when there is a mass over here, there will be some tension in the steel and there must be some tension in the copper, right? Now stress, it says the stress is same. So area of both of it, we are assuming them to be same only, right? We are assuming them to be, so see, uh, okay, so area is also mentioned. Let's assume that area of the bar of the steel is A and for the copper it is 2A. Actually, I missed this data to be given. Now the stress in steel and stress in copper being same. Stress in steel and stress is copper being the same. So stress in steel is what? It is T1 upon area and stress in copper is T2 upon 2A, right? So stress being the same, that means that these two remain the same. Now please understand this. So from here, can we write T2 is equal to 2 times T1? T2 is equal to 2 times T1. Now see, every information that I give you is going to be used in physics. See, now see, we understand, so we need to find this x. Now we understand that any body, so this is a, problem in which there is no unbalanced force. This is an static equilibrium case. So when it is an static equilibrium case, the moments about any point, the moments and about any point must be same. The moment about any point must be same. So moment about any point must be same. So it must be T1 into X and this should be minus of T2 minus of T2 2 minus X and this must be equal to 0. So I have taken the moment about this mass location of M, right? Why? So if any other point I'll take this mass is also not given, so three variables will come, right? Okay. Now see, we are having a relationship. We are having a relationship between T1 and T2. So what we can write, this is T1 x minus T2 is 2 times T1. 2 minus x is equal to 0. So from here, can we write x minus 4 minus 2x is equal to 0? So sorry, it will be minus minus plus. So this will become x is equal to 4 by 3. This is 1.33 meter. Understood, beta? Please answer me. This is going to become 1.33 meter, right? So that is going to be the B option. Is that clear? Please answer me. Bole. Is that clear? Please answer me. Right? Yeah, I'm sure it is clear to all of you. Right, now let us suppose that in this same question, just a moment. So I just okay. So let it be. Let us assume that here we have to find the x. Now strains are equal. Strains in copper and steel are equal. Now, when the strains are equal, what is going to be the x that you have to now tell me? Okay. So let's suppose it is 1 meter. Same options we can keep. So 1.33, no, it is going to be 2.0 meter and then 1.66 meter. Now let's try this one. Let's try this one. So previously the stress was same. Now in this case the strain they are saying are same. Okay. Can you please try it? See, remember whenever location or whenever position of any force is asked, you always must write through the remember you always must write through the what? You always must write through the moments concept. Okay? So whenever a location is to be found, you always need to go for the moments concept. Okay? Now please do it. Please go for it. Please try it. Please do it, guys. So now strains are to remain equal in copper and steel. Please try. I'm very sure we can do. See now, what is we are to have to do? Now it says the strain in both of it are same. So what is the strain? So change in length upon original length, or you can say sigma upon E from the Hooke's law. So sigma upon E of steel must be equal to sigma upon E of copper. Right, so what is going to be sigma? So sigma is T1 upon area, that is A, and Young's modulus of steel is 200 GPa. So this is for the steel, and for the aluminium, the tension is T2, area is 2 times A, and Young's modulus is 100. So from here, T1 is equal to T2. Now here T1 is equal to T2, we can have this equation. So this equation will remain same only, na? If we take the moment, so it will be T1 into X, T1 into X, okay, minus T2 into 2 minus X is equal to 0, okay, is equal to 0. So it will become, so from here T1 and T2 are the same, so can we write this is T1 2 minus X is equal to 0. So from here this will become 2 times, so T1 is cancelled out, so 2 times X is minus 2 is equal to 0, so X is equal to 1. So when the strains are going to be same, they have to be at 1 meter, that is exactly at the midpoint. That is exactly at the midpoint, right? I hope all these concepts are clear to everyone. Is it or isn't it? Yeah. Right. Now guys, please try to understand this. So see, in this session what I tried to do. So for the normal stress, longitudinal strain, a lateral strain, Poisson ratio, all this is completed. So in the next session, I'll be taking you through the new concepts of this particular thing. Like I'll tell you that if certain. So here see, copper and steel are attached somewhat parallel to each other. Now what if they are attached one after other? How the material is going to behave? Okay. Further, we'll be talking about the thermal stresses. Okay, strain energy we'll talk about. Stress strain curve we'll talk about. So all this we'll be talking about in the next section. So guys, please don't forget to subscribe the channel. So we are here to help you in achieving your dreams. So please do subscribe. Okay, and thank you very much for attending the session. Those students who are joining live, also those who are watching the recorded session, also please, if you find this video and this sessions helpful to you guys, please share to your friends also, so that they can also be benefited. Okay, and also like you can also come to the Unacademy app, right? On Unacademy app there are special classes, there are course running very low cost, and special classes are free only, so you can come out the special classes, and you can join the Unacademy app. So there also you'll get a lot of content which will definitely help you prepare better for your upcoming NEET examination. Okay, so guys, don't forget to subscribe the channel. Thank you very much, have a good day, and we'll see you in the next session.